The title of this talk is Meta-Perspective on Heart Rate Variability, Antiquated or Indispensable. This is part 3 of a 5-part series. The first 2 talks are already on YouTube, and this talk should similarly be posted. This is my disclosure slide. As I mentioned in my first 2 talks in this series, this is the way I interpret how HRV has evolved over the past 50 years, and I've divided it into 5 stages. Understanding HRV, HRV as a marker of autonomic nervous system, HRV as a marker of body-wide function, HRV in the construct of mind-body interaction, and HRV itself as a desirable target. Why these categories have been divided accordingly will become clear when this talk series is over, but it reflects the evolution of our scientific approach to HRV, which has been strongly influenced by the prevailing scientific paradigm of the day. So when we talk about the first stage of understanding HRV, this occurred in the 1970s and 1980s, which I believe was a strong age for physiology in general. As a consequence, this is when we begin to understand what biological processes are contributing to heart rate fluctuations, which includes respiratory sinus arrhythmia, baroreflex, and other physiological processes. And this also was a time when we identified the signaling pathway involved in heart rhythmicity and the role that the autonomic nervous system plays in modulating it. This is the time when heart rate variability, time domain and frequency domain measures are established and formalized. And this is a time when we also recognize that higher frequency HRV is associated with the parasympathetic branch predominantly, and the low frequency is a combination of both sympathetic and parasympathetic nervous systems. The 1980s and 1990s was the age for major advances in cardiovascular medicine. This was a time when the autonomic nervous system was recognized as playing a pivotal role in the occurrence of deadly arrhythmias or sudden cardiac death, particularly post-MI. And heart rate variability as a proxy for autonomic nervous system activity was used to risk stratify post-MI patients. And in fact, HRV showed great promise as individuals with lower HRV had marked higher mortality. But with the advent of rapid revascularization and beta blockers, HRV became relatively obsolete. Plus, it was messy. It is confounded by multiple factors, as I had mentioned in part 2 of this series. So within this context, we are now in the 1990s and 2000s, where epidemiology and nonlinear sciences have come to the fore. And I believe that both these disciplines help reframe HRV as a marker of body-wide function, and hopefully by the end of the talk you get an understanding why I say that. The goals of this talk are to review HRV epidemiological studies, understand basic concepts underlying nonlinear dynamics, appraise evidence for fractal-based HRV measures, and summarize other nonlinear HRV measures. We'll start off with reviewing the HRV epidemiological studies. I think we all know what a large observational cohort study is. An example of this is the Framingham heart study, which enrolled its first patient in 1948. Typically, a large number of people are recruited from a community and observed over time and to assess how a risk factor or exposure affects a specific outcome of interest. In our case, we want to see how heart rate variability measures like SDNN relates to development of CV event, cardiovascular event, or death. So the question I put to you is, when do you think these cohort studies get published? If the golden age of cardiovascular medicine began in the 1980s, when do you expect to see the epidemiological studies to come out? To answer that question, I put here the list of the major milestones for the Framingham heart studies, and you could see that some of the major discoveries that we know now as pretty obvious occurred in the 1960s, such as cigarette smoking is associated with heart disease, or high cholesterol, high blood pressure associated with heart disease. You see some of the results sort of trickle in the 1960s and 1970s and 1980s, but it was really in the 1990s that it really picked up, where major milestones were discovered almost on a yearly basis. And if you recall, clinical cardiology made advances in the 1980s, so there's usually a 10 to 20 year lag before advances in the clinical world makes its way into epidemiology. And a lot of it has to do with the time it takes to recruit the participants, to observe the cohorts, and also some practical implementation of some of the new technologies. In the case of heart rate variability, it was the Holter technology. So this was one of the first studies that came from Framingham. This was published in 1996 by Tsuji. The title was Impact of Reduced Heart Rate Variability on Risk for Cardiac Events. They recruited 2,500 individuals. The mean age was 53 years of age. The participants were free of cardiac history, and they obtained 2-hour ambulatory EKGs during the clinical visits and took a look at 3 time domain and 5 frequency domain measures. The primary outcome was cardiac event, which was defined as angina, unstable angina, myocardial infarction, CHF for sudden death or non-sudden cardiac death. And there was a total of 58 cardiac events. And the statistical analysis involved proportional hazards regression analysis. It was adjusted for age, sex, and other clinical measures which were considered important for cardiac mortality or risk. This is the table that came from that study. And there are 2 things that I want you to notice. First, the heart rate variability is presented in logarithmic form, and the reason they did that was because the data, the heart rate variability data itself was skewed. Logarithm enabled it to be normalized and to be able to be applied in the statistical analysis. And the other thing is there's this -100 for these 2 variables. And what they did was they divided the 2-hour recording of the ECGs into 100-second segments. And so the very low frequencies and the total power are of those 100-second segments and not necessarily of the whole 2 hours. And we see here that a few of these variables are significant, including SDNN, very low frequency, high frequency, and total power. However, the one that's associated with the greatest significance is the 2-hour SDNN. So what physiological process does the 2-hour correlate with? And this is a slide that I included in part 1 of my series. And it answers the question, what physiological process does SDNN most correlate with? And it really depends on the duration of the data. And the reason for that is that heart rate variability is distributed largely in the lower frequencies when it comes to power spectrum. So the longer the data that you collect, the more it's going to predominate by the lower frequencies. So 2 minutes associate with high frequency, 5 minutes with low frequency and high frequencies, 1 hour is very low frequency, and 24 hours is ultra low frequencies. So the 2 hours from the Framingham study is more associated with very low frequencies. And the reason the very low frequencies is relevant is because, at least when I had put this slide up in part 2 of the studies, we saw that very low frequencies was highly correlated with mortality after MI. And this graph clearly shows that the very low frequency was much more significant compared to the other higher frequencies. And it also showed in this table here, where the ultra low frequencies was associated with all-cause death, whereas cardiac and arrhythmic death was associated with very low frequencies. The other thing that I wanted to mention from this study was that this was a 2-hour ambulatory ECG acquisition during the clinic visits. This is in significant contrast from what I had mentioned in the part 2 of the series. In part 2, there was a strong emphasis on avoiding factors that influence HRV. I had mentioned that there were many cardiac confounding factors, such as food intake, time of the day, whether you had even drank water or whether your bladder was full. And as a result of that, there was a lot of instructions given to patients, and still are, regarding what they can or cannot do before they undergo an autonomic test. That included no food for 3 hours beforehand, no alcohol for 12 hours before. This very rigid, regimented protocol is in stark contrast to the approach that was taken in the Framingham study, because the individuals, the participants, when they came to the clinic, could actually do whatever they wanted. They could go walk around and they participate in various studies. And so there was no control for these potential confounders. Also, the time of day wasn't exactly recorded, so this could have been done at any time of the day. This dichotomy in the way ECG is obtained really highlights the differences in how HRV is interpreted. A good example of this is something that I encountered myself in collaboration with Harvard OSHA Research Center. We were interested in seeing whether Tai Chi masters had higher heart rate variability compared to healthy controls. And they indeed had higher heart rate variability, particularly in RMSSD. And it was found out the reason probably for the higher heart rate variability was due to the fact that they took slower and deeper breaths. But this led to differences in the interpretation of the higher heart rate variability. One group said, well, the greater heart rate variability does not indicate better health because it is confounded by bigger, slow breaths. Another group, however, said greater heart rate variability indicates better health because he or she takes bigger, slow breaths. So you can see the differences in the way heart rate variability is interpreted. One group says a higher heart rate variability is confounded by different practices, whereas another group says the higher heart rate variability is actually a reflection of better habits. And this extends not only to breathing, but also to physical activity and good sleep as well. So you could see that this difference has started to manifest in the end of the 1990s and 2000s because there's a different type of data that was obtained or used for heart rate variability. One that was very controlled for cardiology and autonomic neurology. Another one that was pretty much free running and in real life conditions. The other thing I would like to highlight from this Tsuji study in 1996 was the participants. There was, in the end, 2,501 participants. But if you take a look at the table 1 of the study, there was up to 3,420 who actually had ambulatory ECG data. But nearly a fourth were excluded, many because they had ectopic or non-sinus rhythm beats. And the reason I wanted to point this out was because expect to exclude up to a fourth of the patients that you enroll in your studies if you're going to evaluate heart rate variability. And if you and for many of the subsequent studies that will be cited in this talk have excluded atrial fibrillation, and it's one of the weaknesses of heart rate variability is that you do have a large segment of the population excluded for these reasons. This is a meta-analysis done by Hillebrand in 2013, which summarizes the studies that looked at heart rate variability in a general population. And we can see here that it was done in numerous locations with a focus largely on SDNN with multiple endpoints, but mostly about cardiovascular death. And there was also others with myocardial infarctions, other cardiac outcomes. Mean follow-up, many of these were large studies. Mean follow-up ranged from 3.5 to 13 years and a good range in age. But the one thing I wanted to point out was the duration of measurements. And the reason why this was important is that these measurements are quite short. And when you have different durations, and as mentioned in SDNN slide, is that the shorter duration indicates higher frequencies, whereas the larger ones are associated with lower frequencies. And so the summary here does not truly indicate the same physiology processes going on. These shorter segment ECGs are also quite sensitive to a number of confounding factors. As I had mentioned in my first part of the series, is that high frequencies and low frequencies has a circadian rhythm, for instance, or it could be affected by stress or other factors. So taking a snapshot of 10 seconds to 30 seconds or a few minutes in a single day will introduce a lot of, we'll just take only a snapshot. And so it is unclear how effective these measures will be compared to much longer term recordings. And so this is the forest plot that shows the effect of low heart rate variability compared to high rate variability in regards to fatal and non-fatal cardiovascular disease. And if we categorize according to the duration of the measurements, we see for these studies, which required data for less than 3 minutes, you see that the relationship in terms of mortality is not as strong. Whereas for those studies that acquired much longer data for 2 hours or 24 hours for both these studies, the relationship is much more consistent. And the Makakallio may not be as consistent because it was a much smaller study. Heart rate variability also has associations or important prognostic informations for post-MI and congestive heart failure as well, not only in the general population. And so the summary of the epidemiological HRV studies is that HRV has significant prognostic implications even in free-running conditions. Lower heart rate variability frequencies are very important, and that's a factor that I think we've ignored over the past few decades. Very low frequencies and ultra low frequencies in particular have not had received much attention as of late. And heart rate variability is applicable to the general population and not limited to specific cardiovascular conditions. In nearly all studies, dysrhythmias such as AFib, frequent ectopic beats were excluded. And various conditions such as use of beta blockers post-CABG may limit HRV usefulness. Now, I didn't really go into the details because I didn't have time to go over this in a 1-hour talk. But post-CABG particularly can significantly diminish heart rate variability even up to months afterwards. And nearly all the studies acquired only a snapshot of heart rate variability, for instance, in a single day or even part of a single day. So it is surprising to me that we even found a significant result in these studies. A 2-minute snapshot in one day for years can really, it's hard to imagine, can really impart any information about mortality. And monitoring dynamic changes in heart rate variability are potentially helpful, but understudied. And this is an example of where the dynamic changes can really be important. This was a study done by Adamson in 2004 and took 288 CHF, congestive heart failure patients who had very advanced congestive heart failure. They had an implanted cardiac resynchronization device, and this device is able to track the atrial beats and to see if there was an actual normal sinus rhythm. And what they did is they evaluated a certain heart rate variability measure called SDNN. It's a standard deviation of 5-minute median atrial interval. It is a type of very low frequency measure, and they measured this across the days, and they've done this up to 2 to 3 months and even longer. And they've noticed that when it came to a hospital admission, the heart rate variability measure decreased steadily right before the hospitalizations, indicating a route towards decompensation. They also saw a rise in the night heartbeat and also a decrease in the patient's physical activity. They created a detection algorithm for this decompensation in CHF. Essentially, they took a mean and then found the periods where you had consecutive decrease below the mean, and you had accumulated difference, and then they decided what threshold would be to activate this decompensation algorithm. And this decompensation algorithm did a great job in detecting those individuals who ultimately got hospitalized. It did a better job than physical activity and even night heart rate. And finally, modulation of higher heart rate frequencies has been effectively ignored. This was a study that I cited in the part 1 of my series. This was a comparison of post-MI patients, those with high heart rate variability and low heart rate variability. The individuals with high heart rate variability had higher heart rate variability because they had significant circadian modulation of the high frequencies throughout the course of the day, whereas the low heart rate variability individuals did not. And this modulation of the high frequencies and low frequencies of heart rate variability is largely ignored now, and it's something that I think is worth evaluating again. And importantly, the modulation of high-frequency heart rate variability is not captured in the very low frequencies or ultra-low frequency amplitudes. The next part, we'll take a look at understanding basic concepts underlying nonlinear dynamics. It's important to know what linearity means. Linear systems tend to generate very predictable responses, so linear systems have a proportional response to its input. Nonlinear systems, however, tend to produce nonlinear responses, things that are not in direct proportion to the input. and these are various examples of nonlinear output. And what differentiates nonlinear systems from linear systems is that you can get all different kinds of output to a specific signal. A linear system, for instance, gives a very similar signal to the input here, which is sinusoidal. A nonlinear system responds differently to the sinusoidal system. It could be periodic, quasi-periodic, or even chaotic. These are for higher order nonlinear systems. And nonlinear dynamics has quite a rich history, and this even extends back to the 1800s to Poincaré. But a lot of wonderful work, rich, amazing work was done by the Soviet Russians in the 1920s. Chaos theory was started approximately in 1960s by Weda and Lorentz. Lorentz was at MIT and popularized the term butterfly effect. You had Arthur Winfrey, who studied nonlinear oscillators in biology, and Manopro, who popularized fractal geometry and fractals. But it was really in the 1980s when you had widespread interest in chaos, fractals, oscillators, and their applications. And this sort of disseminated, diffused into the medical field into the 1990s. And in the early 1990s, some scientists like Ari Goldberger and Bruce West speculated that certain characteristics seen in chaos theory and nonlinear dynamics might underlie some of the unique features seen in biologies. This includes the fractal characteristics that we see in the GI tract, in the lungs, and also the heart. And this extended also the temporal complexity as well. And this is an example of a heart rate time series that obtained in 300 minutes, where you could zoom in the 30 minutes range and also into the 3-minute range and recognize that there is this fractal nature to it, essentially this repetition of patterns across spatial and time scales. The question is, how do you show that biological systems display nonlinear plus or minus chaotic dynamics? And that was certainly a difficult question to answer. Initial attempts were made to apply certain principles of chaos theory, such as period doubling or bifurcations, Lyapunov exponents, correlation dimensions, or embedding dimensions to biological systems. However, the problem is that deterministic chaos theory applies much more easily to simple systems that display complex behaviors. An example of this is a double pendulum that's shown here. And so on the other hand, biological systems are quite complex. It's not a simple system that demonstrates complex behaviors. It's a complex system that demonstrates complex behaviors. And so what is the theory that is best applies to biological systems such as heart rhythms that's quite complex and regulated by multiple processes? To me, probably the most useful analogy or theory from complexity theory is criticality theory. And an example of criticality theory is the Ising model. And hopefully you'll get an understanding of what the criticality theory means based on this example. Now, the Ising model is a representative model of ferromagnetic magnetization. Each grid here represents an atom which could be aligned in one of two conformations, either black or white, or in this case, up or down, +1 or -1. The total magnetization of the system is essentially the average of all the spins. And it's the dynamics of the interactions between the atoms is what makes this model interesting. So if you have two atoms aligned together, they share the same sign and the total energy is decreased and thus favored. If the two atoms are opposed or opposite, then the energy is increased and unfavored. And H represents the total energy of the system, but each spin has its own energy, which determines which conformation is favored. This relationship is further influenced by temperature, and the higher the temperature, the more likely the spin is likely to flip, regardless of its intrinsic energy. The Ising model is very useful to understand the magnet's response to temperature. And this is a graph of magnetization versus temperature. And we can see here at the very low temperatures that the magnet has either a positive or negative conformation, either north or south. And so there is a net magnetization. However, at higher temperatures, because of the frequent flipping of the ferromagnetic atoms, you have a net magnetization of 0. However, it is at this criticality location where it's between absolute magnetization to no magnetization where you see some very interesting patterns. And this is where you begin to see fractal or self-similarities. And this is an example of this, where you could take a segment from this critical threshold and you could zoom in within each other. And all four of these patterns look quite similar to each other, but they're existing at different scales. And so this explains the term self-similarity or scale invariance. It's at criticality that we see this power law relationship. And this power law relationship is described by this equation. An example of this is cluster size. And if you figure out the distribution of cluster size, you would notice that you have much more frequent smaller clusters compared to larger clusters, and this logarithmic relationship shows this linear response because of this exponent here. And you see this power law in multiple situations, not only in the cluster size, but also the dynamic correlations between spins with respect to distance, and also the temporal variation in overall magnetization. In fact, these two characteristics, fractals and power law, are related, and it can be seen in this equation alone. And f of x is equal to x to the minus alpha. Let's just say you scale up by a factor of c. You scale up by a factor of c, and the cx enters here. And then you factor out the c from this parentheses, and then you get this relationship here because x minus a is this f of x. But again, you see that even at a larger scale, the f of x remains the same. And this explains the fractals. Basically, at different levels of scale, you have the same appearance of the function. And this power law is quite ubiquitous. And an example of this is the population of the United States, of United States cities. If you map out the distribution of the population of cities by frequencies, you again see that the bulk of distribution occurs for small sizes in small towns, whereas a small number of cities with much higher population produces the long tail to the right. And again, this follows a power law relationship. And in order to see if it's truly a power law relationship, you take the log of both. You take the log of the population, log of the probability, and you should get a linear relationship with a slope of minus alpha. And this power law is seen in many different situations, all across nature, as well as complex social networks, and also even in books. The word occurrences in Moby Dick's also follows a linear relationship, number of citations to a scientific paper, number of calls, magnitude of earthquakes, the diameters of craters of moon, etc. So this power law is a ubiquitous law that's seen in complex systems. This complexity, or this fractality, can also extend not only from a spatial situation, but also temporal situations by time. And again, another example of this where you sort of zoom in and see the similar patterns despite differences in scales. In regards to time-based data, the particular relationship that's most important is something called 1 over f power spectral density. It's 1 over f because the power is inversely related to the frequencies. The higher frequencies tend to have lower power, whereas the lower frequencies has higher power. And certain types of noises can be categorized according to this relationship. White noise is something that has power spectral densities that's uniform across frequencies, whereas the other extreme is brown noise, which has much more of a lower frequency component. And it's this halfway point between these two, which is called pink noise. And it's this pink noise, 1 over f, that is of great interest for us. Peak noise, just like the power law in spatial frequencies, is quite ubiquitous. And you can see this in multiple artificial as well as natural settings. You can see this in vacuum tubes, semiconductors, and for natural settings, human hearts, squid axons, as well as MEGs and EEGs. Question is, how do these fractal and power law properties arise? And so this is the million-dollar question to which scientists are still trying to figure out. We still don't have the answer. But there's some really critical ingredients for these nonlinear properties to occur. And first is a balance between order and disorder. Criticality occurs when there's both a stabilizing force and destabilizing forces. And the balance of the two creates these really dynamic characteristics at criticality. The second thing and third thing that's involved is nonlinearity. There needs to be some kind of nonlinearity in these fractal systems. And particularly for this Ising model, it probably is found in the energy function itself. And the other thing is iterative feedback, that you have, for instance, one spin affect another spin, and then that spin can affect that other spin back again. So you have these iterative feedbacks which can be positive or negative. So fractals and power law properties probably arise from a tug of war between stabilizing and destabilizing forces, nonlinearity, and feedback. So knowing this, which of these cases are healthy? You can see the time series or heart rate over time in 4 of these examples. And for the ones that, for this one that has absolutely no variability, it's congestive heart failure. This one has a periodic variability. This is also congestive heart failure. And this has a lot of variability, almost like a randomness to it. And this is atrial fibrillation. And this is the healthy case where you have a combination, basically the balance between order and disorder. You can take this a little further and say that if health is truly a balanced state between order and disorder, then disease has got to be a pathological breakdown into order, severe order, and then severe disorder. We can ask then, how can you objectively quantify this healthy dynamic? And you can make this logical step. First, if good health is truly a balance between order and disorder, and this is just like a system at criticality, and if a system at criticality demonstrates fractal properties, then truly good health must have fractal properties. And since this is a time series, what we're interested in is something called pink noise, which is a balance between the white noise and brown noise. And the nice balance here is similar to the pink signals that we see here, whereas the breakdown into disorder is similar to white noise, and the breakdown into order is brown noise. The next part is to appraise the evidence for fractal-based heart rate variability measures. The first study that looked into fractal relationships in disease was bigger in 1996, which was published in Circulation. He had 3 groups. One with a recent acute MI. He had 715 subjects in this group. Healthy group, which had 274 participants. Heart transplant individuals, and there was 19 in this. He took a 24-hour continuous ECG and evaluated the power law slope, which is essentially the power spectral density versus frequency, but paid specific attention from 10 to the -4 to 10 -2 hertz. And the reason for that is that if you take a look at the spectral density relationship of the heart rate, you see a linear relationship or linearity that exists pretty much from the very low frequencies all the way to maybe about 10 to the -2. And then you have these squiggly parts that correlate with the higher frequencies. Bigger et al. Showed 3 examples from each group. This is a healthy individual. This is a myocardial infarction individual and heart transplant person. And this person who is healthy had a slope that was close to -1, again following the 1/f pink noise characteristic. However, the myocardial infarction individual had a steeper slope at minus 1.2, and the heart transplant individual at minus 2.2. The other thing to note is that the total power was significantly different. The one with a healthy individual had higher power compared to the MI and the heart transplant patients. If you take the average for all the individuals that were within this group, you find that these differences in slope and the total power are statistically significant. And again, the healthy individual has a slope that's nearly close to minus 1, which mimics or resembles pink noise. And the same applies to the total power. And this is a representation of the summary of the power law relationships across the three groups. We can see that the healthy group has an overall higher power compared to the myocardial infarction and the transplanted patients. And you can see this from the perspective of very low frequency and ultra low frequency. Again, healthy has a higher very low frequency compared to MI group and the transplanted patients. But this graph also indicates how the total power differentiates itself from the fractal slope, or 1 over F power law relationship. The power law relationship more looks at the distribution of the energy of the heart rate variability across the multiple frequencies. And it's not necessarily relating at the absolute value, but more so how these values are distributed across the frequencies, with the transplanted patients having much more of the power dedicated to the very low frequencies, ultra low frequencies, compared to the very low frequencies. And again, the healthy individuals and partly the myocardial infarction individuals had much more of a peak noise relationship, whereas the transplanted patients had much more of a brown noise type of pattern. And this makes sense because transplanted individuals tend not to have too much heart rate variability, and they tend to have a smoother graph, again resembling brown noise. This is a graph that came again from that same publication by Bigger et al. In 1996. This is a survival graph for the MI group, which numbered 715. And we see here that for those individuals or those groups, individuals that had both high heart rate variability power and a normal slope, which resembled pink noise, their survival, they had higher survival overall and lower mortality, whereas those individuals with low heart rate variability power had worse mortality, and the same also applied to those with a slope, power law slope greater than 1.372. A combination of both these factors, total power and power law slope, had much worse mortality overall. And this indicates to me that absolute total power and 1 over F slope likely contains different information, and the combination of both may be clinically useful. This is a forest plot obtained from Sen et al. In 2018, which summarizes the application of power law 1 over F slope to multiple conditions: MI, left ventricular dysfunction, non-cardiac conditions. And we see here generally that the individuals who died had a higher slope or more of a negative slope compared to those who remained alive. And this relationship was, significant if you combined all the factors all together. And these are figures that were obtained from the studies that were listed in the meta-analysis. And you can see here again a steeper slope indicating a slope less than minus 1.5 indicates higher rates of mortality. And this occurred in post-myocardial infarction, low ejection fraction groups, elderly individuals without past medical history of cardiovascular disease, and even post-stroke. The power law 1 over F slope, however, has certain limitations. First off is that it does not assess short-term heart rate complexity. If you recall of this graph, the linearity, the linear relationship between frequency and spectral density occurred only from the very low frequencies down to about 10 to the minus 2 hertz. It's the shorter frequencies, the short-term frequencies, that really were not included in this power law relationship. And because we focused on the very low frequencies, it requires a significant amount of data acquisition and it requires data more than 24 hours. And the other thing is that power law slope requires the fast Fourier transform, and the fast Fourier transform is not ideal for non-stationary data. And what do I mean by that? Non-stationary data has the mean or standard deviation that changes with respect to time. So you can see, for instance, if you take a segment here, the mean and the standard deviation is very different from here, where you have, low RR interval average, but and also low standard deviation. It's just simply one of the weaknesses of fast Fourier transform. So to address these limitations, C.K. Peng, who is a good friend and mentor of mine and also a scientific advisor for Labfront, published this in 1994. And this was the first study that looked into something called detrended fluctuation analysis. This is something that C.K. had developed. It's based off of a Hurst exponent. A Hurst exponent is a marker of memory and persistence. And unlike the 1/f power law relationship, it is a time domain based analysis. The power law is a frequency based analysis. The DFA is a time domain based analysis. And this DFA is amenable to non-stationary data, and it is quite computationally simple. And to explain how the DFA is done, you, for instance, take this heart rate data, or in this case, interbeat interval, and you do it by beat number here. You take it and you integrate it. You integrate the mean-centered data to create much more of this graph, which tends to be a little smoother. And you divide this data into epochs. The epochs are based on scales. So if you had a scale that was of 10, each epoch would be divided into 10 points. If you had a scale of 100, then each box would be 100 data points in size. And for each epoch, you detrend it and you calculate the root mean squared. In other words, you find out the fluctuations that occur around this linear fit. And then you average all the root mean squared across all the epochs. And then you do the same thing. You repeat 2 through 4 for different scales, and you get this relationship where you get the fluctuation versus the scale, and you get this linear relationship. And what's considered healthy? A healthy DFA relationship is an alpha of 1.0, whereas a unhealthy, or in other words, something that has significant white noise, which they sort of simulated by randomizing the data, the alpha is 0.5. This graph shows the relationship here in terms of pink noise, brown noise, and white noise. And the pink noise has, again, a slope of 1, similar to the power law relationship. However, white noise has a smaller slope. Brownian motion has a higher slope. And this is a comparison between the two. And you could clearly see that there is a difference between the two in terms of the directionality. However, the pink noise, or alpha of 1, is balanced between these two extremes. And the reason there's a difference in the directionality in the direction of the slope is that DFA has the lower frequency represented by the higher scales, whereas the power law slope, the lower frequencies occupies left of this graph. So if you take a look at Brownian motion, which is dominated predominantly by low frequencies, you can see that this has a higher slope in the positive direction, whereas in power law, it has a negative slope here. There is a mathematical relationship between these two, where beta is 1 minus 2 of alpha 2 here. When C.K. Peng applied DFA to normal and congestive heart failure patients, he found an interesting observation here. This is, again, the DFA graph, which maps fluctuation with respect to scale. This is a normal individual's graph versus the congestive heart failure individuals. But you see here something which he termed the crossover phenomenon, where you have a change in the slope. And this occurred in both the healthy individual as well as the congestive heart failure patients, but it occurred in a different way for each. But I think it's good to note that this crossover phenomenon occurred pretty much in the same region where we had this change from linearity to not linear relationship in the power law 1 over F graph. And the question is, what is the significance of this particular frequency, which is around 0.03 hertz or so? The physiological significance of this crossover phenomenon is unclear, but there must be something that's happening at the 0.03 hertz region, approximately, which leads to this different relationship in this crossover phenomenon. And I think that's something that's worth exploring for sure. But if we take a look at, because there's different relationships, different slopes, C.K. Peng divided DFA into two parts, alpha 1 for the higher frequencies and alpha 2 for the lower frequencies. And for the healthy individual, it's interesting that the slope is close to 1, so it resembles peak noise, whereas what's considered healthy is of slope greater than 1, or even more so in the Brownian region. Whereas the congestive heart failure patients tend to have white noise like alpha 1, whereas the alpha 2 is much more Brownian. So this is a summary forest plot put out by Sen in 2018. Again, looking at DFA alpha 1 specifically in regards to mortality across multiple conditions, myocardial infarction, LV dysfunction, non-cardiac conditions. And you could see that alpha 1 in the deceased tends to be lower compared to the alpha 1 in those who remained alive. And this relationship, this comparison between those deceased versus live remained quite significant, statistically significant across all these studies, none of which crossed over for equivalency for any of these studies. To summarize heart rate variability fractal measures, I would say that fractal measures have prognostic implications even in free-running conditions. Again, just like I had talked about in this previous epidemiological studies, the heart rate was collected using 24-hour Holter monitoring. And again, this was done in free-running conditions without any restrictions about what the participants can or cannot do. Heart rate variability is applicable to the general population, not limited to specific cardiovascular conditions. And in power law 1 over F and DFA alpha 1 frequently outperform traditional heart rate variability measures in predicting mortality. I didn't really go into too much details, limited by the time of this presentation, but it seems that this was specifically consistent across multiple studies and more so in the era of beta blockers, which tended to affect the traditional heart rate variability measures a little more. The other interesting thing is that power law 1 over F tend to correlate more with all-cause mortality, whereas DFA alpha 1 correlated more with cardiac mortality. And this is an example of this. This was a study by Makakallio in 2001. It was a study that involved 325 elderly individuals in Finland, 24 hours of continued ECG with a follow-up of 10 years. And they evaluated DFA alpha 1, power 1 over F, and SDNN. And the first thing to note is you could see this table, which again categorized in all different kinds of mortality, all-cause cardiac death, sudden cardiac death, cerebral vascular mortality, and non-cardiovascular mortality. And you can see the first thing is that the SDNN, when entered in a model associated with these other power fractal or fractal measures, it tends to be all non-significant. I guess, again, indicating that these fractal measurements may have more of a predictive power than standard traditional measures. And then the other thing to note is that when it comes to non-cardiac mortality, for instance, all-cause or cerebrovascular or non-cardiovascular mortality, the power law slope tended to do a better job compared to DFA alpha 1, whereas DFA alpha 1 did better overall in terms of cardiovascular prediction, and this includes cardiac death and sudden cardiac death. But in regards to DFA, it is more related to LF over HF ratio, and this is shown in Makakallio, published in 2001 in JACC. These are 3 examples. This is a healthy individual, for instance. This healthy individual had an alpha that is close to 1, which is close to peak noise. And the reason this individual had essentially high long-term variability and normal short-term variability, which is expected of peak noise. On the other hand, this individual had more of a Brownian picture with more higher lower frequency power compared to the higher frequencies. And this is an individual that has more of a white noise picture where you have frequencies that are much more distributed uniformly across all the frequency ranges. But the relationship can be clear when you see where the lower frequency is represented in the DFA graph. The lower frequencies is occupied here, and the higher frequencies is in this region here. So if you have a predominance of lower frequency, then you would anticipate having a higher frequency as you do in this example here. And then the converse is true here, where you basically have more of a higher short-term variability, which is represented here. So again, DFA is correlated with LF over HF ratio. However, that does not maintain its relationship in free-running conditions simply because DFA is more attuned for non-stationary data compared to Fourier transforms, which is used for low frequency and high frequency ratios. So DFA alpha 1 still remains more advantageous for that reason, particularly if you're going to apply it in real-world practical situations. And in nearly all the studies, dysrhythmias, AFib, frequent ectopic beats were excluded in these studies, just like the epidemiological studies. And so, again, expect to exclude a number of individuals if you are going to implement fractal measures in your studies. But it is also worth including some of these individuals to see how AFib does affect these fractal measures, because these fractal measures are essentially based on the idea of a balance between order and disorder, and AFib is a disordered state. So I can't see why we cannot include these individuals in your study. And just like the epidemiological studies, nearly all the studies required only a snapshot of heart rate variability. These were obtained on a single day, which was then carried over to figure out the mortality, which lasted for years. And monitoring dynamic changes in heart rate variability are potentially helpful but understudied. And an example of the utilization of dynamic changes in fractal correlations can be seen from this more recent application of DFA alpha to exercise. This was published by Bruce Rogers in 2021 in Frontiers in Physiology. And in this case, there was a ramp up in exercise given over time to the point where you reach a lactate threshold, the first threshold. And you can see that around the same time this lactate threshold is reached, the DFA starts to decrease. And according to Bruce Rogers, there is a cutoff of 0.75, which correlates to LT1, or in other words, the threshold of the lactate buildup. This is, not established. Certainly, this group has published a number of other studies, but this is, probably needs to be validated. Finally, we're in an era of wearables and large public and private data sets. An example of large public data sets include All of Us, which is the precision medicine initiative by the NIH. There's a Million Veteran program within the VA administration or the VA programs. And then you certainly have private data sets such as EPIC and Cerner. And many of these are considering incorporating wearable devices in their data sets. And this data set will also include other information, not only clinical conditions, but also genetic information and a lot of blood and biochemical biomarkers. So we're entering in an era where these wearable related variables, such as heart rate variability, will be found in concomitant simultaneously with other measures related to health. I think we're entering a golden age of understanding a lot of the heart rate variability relationships with medical conditions and also overall health. So I think we're entering a very exciting time for this reason. And heart rate variability for this, which is dynamic, which is shown to be associated with mortality in numerous conditions, will probably regain a lot of attention, and some of the attention will be directed towards the things that have been neglected before. That includes the very low frequencies, the ultra low frequencies, the fractal measures, for instance, or the dynamic modulations of these variables in across the course of the days, the weeks, months, and the year. So I think this is a great time to enter heart rate variability research, given these developments, these large scale developments that we're seeing overall in research. Finally, I'd like to talk or summarize other nonlinear heart rate variability measures. Given the limited time, I am not going to go into all the other alternative nonlinear measures in great detail. But the one that has probably received the most attention is multi-scale entropy. Multi-scale entropy assesses the regularity of the signals, and it's done over multiple scales. And how regularity is assessed is by using something called sample entropy. And sample entropy assesses the relationship, sort of the consecutive ordering of the data. So in this case, you take a look at these first 2 points and you identify in the subsequent data sets later on is to see, like, where do you see similar relationships occur? And so you can see that you have one occur here and another one occur here. But then you could also see for the third point in this relationship, you see something that's blue here. And so you try to see, again, do you see the same subsequent ordering in the other identical sets? And you don't see that here, and so this one's not included, but this one certainly has that third consecutive point which matches this. And so the sample entropy is essentially, out of the two possibilities of similar options, you have one that appears similar like this. So the lower number of similarities that you have compared to the available options will lead to a higher overall sample entropy. So a higher sample entropy is attributed to greater irregularity of the signal. And you do the same approach, but you do this across multiple scales, again, similar to the DFA scaling as well. And what you get is graphs such as this, and this is an example of one which was taken from Physical Review's letter in 2002. You have healthy individuals, which is represented by this green graph, atrial fibrillation in this graph, and then congestive heart failure in the circle graph here. A healthy individual, so atrial fibrillation individual tends to have a lot of the irregularity occur in the very low, in the high frequencies, but then as you sort of go out into the lower frequencies, then you start losing that irregularity. However, for congestive heart failure, you tend to have low amounts of regularity across all temporal scales in both low and high frequencies. And the healthy individuals, however, maintains high amount of irregularity across all temporal scales. And this could be extended to differentiating between the young and elderly. Young individuals have an overall greater irregularity or sample entropy across all the time scales compared to the elderly. So if you take a sum of all these values across all the scales, the sum MSE or the multi-scale entropy tend to be larger in the young individuals compared to the elderly. Another nonlinear measure methodology is the symbolic dynamics. Symbolic dynamics, just like MSE, does care about the consecutive ordering of the RR interval data. but they use symbols in order to describe sort of the patterns that we see here. And you could see, for instance, there are different patterns here, some that has very low variability, one that sort of maintains some consistency, but then later some variation, and then one that has variations in both consecutive measurements. And what this study published in 2005 by Guzzetti showed that those individuals with higher numbers of zero variance tend to be more prone to arrhythmias compared to those who did not get arrhythmias. Another type of relationship or type of methodology is the Poincaré plot analysis. What this does is you map out the one RR interval, compared it to the subsequent RR interval. And from this graph, you could you get these plots, and you try to extract the elliptical fit for that, and then you extract SD1, which is the short axis for this ellipse, and the SD2 is the long axis of the ellipse. From my perspective, Poincaré plot is most useful for detecting noise or ectopic beats. And this is an example of why you could detect these ectopic beats. You normally have these normal beats, which have usual RR interval, but then when you have an ectopic atrial beat, you have a short RR followed by a long RR interval. So as a result of that, this short RR may be mapped out in this region here, and then it's followed by a larger RR interval. And so you could see these possible ectopic beats. And then certainly this large one is followed by a regular one, so you could get another ectopic beat or another plot in this region as well. In truth, SD1 and SD2 can be derived by using just simple time domain measures. SD1 squared, for instance, is equal to 1/1/2 of standard deviation squared. This is a time domain measure. SD2 can also similarly be derived using just time domain measures itself. So you do not necessarily have to plot these graphs out in order to get SD1 or SD2. Here are my personal thoughts on nonlinear heart rate variability. Enthusiasm, in truth, has faded over recent years, and there are a number of factors for that. First, you need long-term recordings, and if you remember for power loss 1/f slope, and specifically, it's required at least 24 hours of data, and that also remains true of DFA alpha 1. And the other reasons why enthusiasm has faded is that a lot of the study has been limited to centers with advanced knowledge in engineering and computer science. In fact, most of the studies that were done, and the major studies done for DFA alpha 1 were done in Finland, particularly by the University of Oulu and Medical Center there. There are very few other centers that did look into this in great detail, but not too many. The other limiting factor is it's quite sensitive to adjustable parameters and pre-processing and denoising steps. That's something that needs to be elaborated further. There's also limited info about reproducibility, probably due to some of these adjustable parameters, but also due to noise from the signals itself. And probably the biggest problem in regards to nonlinear heart rate variability is it's difficult to understand from a physiological standpoint. What is attributing to a Brownian noise or a white noise signal, for instance? It's something that we have not fully established yet. And for this reason, it's unclear how clinical care is going to be changed. Like, what can we do to improve it? If we really don't understand the physiological basis for it, then it makes it hard for us to figure out what to target in order to treat it accordingly. But from my opinion, there's clearly something there. We've seen that nonlinear heart rate variability measures have often outperformed the traditional heart rate variability measures in regards to mortality in a number of situations and conditions. And we're seeing that, nonlinear measures are being increasingly available and accessible to ordinary citizens by apps and data availability. I think the intra-individual day-to-day variations will likely use personal specific information. As I mentioned, this is an area that has been understudied. The dynamic changes that we see in heart rate variability, not only of the traditional, but also the fractal related measures, have not really been evaluated in great detail. And just like the application that we saw for lactate thresholds for exercise, I think the same can be extended to many other conditions. And it's an understudied area. And with the availability of wearables and apps and etc., there's going to be, I would predict, much more activity in this area. And DFA alpha and these fractal scales and nonlinear measures can potentially reveal insights into energy allocation distribution across organ systems. The theory behind a lot of these measures is that you have a heart that is sensitive to systems that operate across multiple time scales. So, for respiration that operates in certain scales, higher scales, you have baroreflex that operates in lower frequencies. Then you have thermal regulation and renin-angiotensin, which operates at the very low frequencies, etc. So if you have a heart that functions well, it operates all across all these scales, and the nonlinear measures should do a particularly good job of assessing all across those scales. And I think as we pay more and more attention to positive health and not just purely on disease, some of these nonlinear measures, which track much better to positive health overall, will receive much more attention. So I think there's a lot of excitement in nonlinear heart rate variability, and it's something that I think we should pay attention to in the future. So hopefully you could see why I presume that heart rate variability can be used as a marker of body-wide function. First, it has been applied in ecologically consistent environments. It's obtained in usual living, free-running conditions. There's no need for controlled settings. And the other thing is that there is no single temporal scales. The heart interacts across different organs with different time scales. And we've seen this particularly with the fractal measures. And the heart rate variability measures certainly focus on dynamic patterns that emerge across multiple time scales. So, in comparison to the 1980s and 1990s, where the focus was primarily on autonomic nervous systems, the heart rate variability started to focus now on the human body overall and its function in usual day-to-day living. So I think from this perspective, this is why I think heart rate variability serves as a marker of body-wide function. This is the list of references that I had read in preparation for the study, and this is something that I can make available in a Dropbox folder for those who are interested. Thank you for following through with this long discussion. If you happen to have any questions, feel free to reach out to Labfront. And we could, help out to see if I could answer any of those questions specifically. Thank you very much.